Hi everyone, my name is Mike. His name is Mr. Plant. Pretty sure it's a guy. Anyway, in this course, you will get a gentle introduction to using the Python programming language to learn a branch of mathematics called linear algebra. Linear algebra is all about organizing numbers into vectors and matrices in order to implement computations. Linear algebra powers statistics, machine learning, deep learning, AI, telecommunications, signal processing, computer graphics. Pretty much any computation that is done by a computer is done using linear algebra. Programming is a really powerful way to learn mathematics, particularly if you think you are not very good at math. So the purpose of this course is to give you an opportunity to see if you'd like to pursue studying mathematics using coding. This course has a little bit less than 2 hours of video instruction, and every video has a coding exercise at the end. So if you do all of the exercises, then the whole course altogether is probably around 3 hours of time. At the end of the course, you will either realize that you really like learning this stuff, and then you can take more advanced courses that will really teach you how to be a mathematical programmer, or you will decide that this isn't the right path for you, and that's totally fine. It's much better to spend a few hours in a free course to figure that out than to spend a bunch of money buying a bunch of books and a bunch of courses, struggling through them for hours and hours and hours after days and weeks, only then to finally realize that this isn't the right thing for you. You don't need any previous experience with coding or with linear algebra to complete this course. The only thing you need is motivation and willingness to commit 3 hours of your time to learning something new. You got nothing to lose, so come join the course. Welcome to this course. I hope you are excited to spend the next 2 or 3 hours learning about Python, learning about numpy, learning about using Python as a tool to learn mathematics, in particular, a bit about linear algebra. In this video, I'm going to show you how to connect to Python online so you can participate in the coding exercises and follow along with me in the lectures. So what you do is you go to this website, jupiter.org/try. Just be mindful of the awkward spelling. This is not Jupiter the planet. Okay, you're going to get to a site that looks like this. There's a couple of buttons. Now, it might change slightly over time, but there's going to be some button, might be the top left, that says try Classic Notebook. That's the one you want. Classic Notebook with the blue and yellow snakes on it like this. So we click on this, and that's going to open up another site called Binder. Now, it might take a minute or so to load. And if you get an error message, if you don't get to a page that looks like this, and instead it says that something about the servers being full, then basically just wait 30 seconds and try again. Refresh the page. Eventually, you will get through to a website that looks like this. This is our main Python window, and we can interact with Python here. Now, this main page here already comes with some introductions to using Python notebooks and Python in general. So you can click on these. These are hyperlinks. We can do, notebook basics. And then we can go through and sort of read this and basically do what it says and learn a little bit about the Python notebook. Now, if you want to do that on your own, that's fine. If you are curious to learn more about Jupyter Notebook, then go for it. You can go through all of these. But just to be clear, you do not need to go through these for this course. I'm going to tell you everything you need to know for this course. So this will be just, if you want to learn more on your own. So when you get to this site, you go up here, click on File, and then New Notebook and Python 3. And then this is going to open the main Python window that we are going to be using in this course. So this is called a cell. This is where you can write code. Let's see, like 3 plus 7. And I'm going to press on my keyboard, Control Enter. And you can see that gives me an output of 10. Now I'm going to talk more in the next video about what this means, how to interact with all this stuff, and so on. The main thing I want to tell you here is about saving these files. So the thing is, we are not actually running Python locally. This is not running Python in the browser. Instead, this is running a session of Python somewhere on a remote server. I don't even know where it is. It's on planet Venus or something. It's somewhere else. Now, the thing is, this server could cut you off. Maybe there's going to be a server overload. Maybe you're going to have some, the internet is going to hiccup. Or what also happens, if you spend too much time idling, I think it's 15 minutes or something. If you spend 15 minutes or whatever the time limit is without doing anything, without interacting with Python here, you are going to get cut off from the server. Now, I really do not want you to be in a situation where you spend, half an hour writing really great code, you're working really hard on the exercises, and then you lose the connection to the server. So make sure to save your work and then download it. You can download this entire window, all the code that you've written. You can download it here by clicking this button that will download it automatically. If you use GitHub or Binder, you can also connect with those and then store your scripts on GitHub or Binder. If you don't know what these are, then don't worry about it. It doesn't matter. You can also click on File, Download As, and then you want to download as a notebook. So you can see there's multiple formats here. You want the notebook, .ipynb. This is for IPython notebook. And then once you've downloaded this, if you need to, you can go here back to File, Open, and then that's going to open this other window, which is actually listing all of the files that we have in our current session. And then you can click here on Upload, and then that's going to allow you to select a file on your computer. So then you can select the file that you've downloaded, and you will see that file here. And then you can click on that and you get back to the file that you were working on before. So again, just to reiterate, this is not Python running locally on your browser. This is Python running on a server. This file is in your browser, but as soon as you close this file, or if something happens with the connection with the server, you could possibly lose your work. So don't forget to save it, connect to a service, or download the files so you can re-upload this again so you don't lose your work. Okay, so I actually recommend for this course going through Jupyter online just because it's easy. I want the entry barrier to be low. You don't have to install anything locally on your computer for this stuff to work. All that said, if you are going to be more seriously using Python in the future for other more longer or more in-depth courses, if you're going to be using Python for data analysis or statistics or whatever your web development, anything, then I actually recommend downloading Python and running it locally on your computer. The best way to do that is through the Anaconda package. You can get to it at anaconda.com, and then you would go to individual edition, and you have to, let's see, find, download. There's a couple of things you have to click here. So it's going to be, depending on your operating system, and then you basically always want Python 3, not Python 2. And I'm not going to go through all of the installation and how to use it installed locally on your computer, because in this course, I want to keep things simple, which means I'm going to keep things online. But I'm just letting you know about this in case you decide after this course that you really are serious about learning Python. Then it's probably best to shift from doing everything online to doing everything locally on your computer. So let's get started by creating some variables and doing some really simple arithmetic. So first what we need to do is make sure that we're actually going to be typing inside this cell of code here. Notice that it's blue, it's highlighted in blue here, and then when I click inside the cell, it turns green. That's how we know that we are typing actively inside this cell. Notice also that this is empty here, and in between these square brackets, it's empty. You're going to see that change in a moment. So I'm going to type a equals 3. Now so far, that doesn't do anything. We haven't really run any code, we haven't created any variables. This is just some text on a screen. What we need to do is tell Python to actually evaluate this code, to run this code. Now, there's a couple of ways to do that. One of which is to press the run button here. So that's going to run whatever cell is the active one, whatever cell you're currently typing in. Now notice that this number changed to a 1. It was blank. It looked like this. And now we get a 1 here. So that tells us that Python ran all of the code inside this cell, and it labeled it as 1. And you'll see we run it again, and it's going to become a 2. So each time you run a cell, or each time you run some code in Python, Python will update this counter, and that just lets you know how many lines of code you've run. Okay, now this you can do, but I find it gets a little bit tedious because you keep having to use the mouse and so on. A shortcut, a keyboard shortcut, is you press Control-Enter on your keyboard, and notice I pressed Control-Enter, and then this turned into a 2. Now a few other little keyboard shortcuts are handy as well, and you'll learn those a little bit later in the course. Okay, so now we've created this variable, but what does that mean? What is this variable? So what we've done here is assign to the variable a the value 3, or the number 3. So now I'm going to type a again without any other assignment, and now we get an output. We didn't get that before. So now we have an output, and that's because here Python doesn't think that we are interested in seeing anything. And here, when we don't have an assignment like this, we just have the variable name on its own, then we get the output. So we see that the value of a is equal to 3. So there's more that we can do with this. We can say a plus 2, and that's going to give us an output of 5. So a corresponds to 3, and then plus 2 is 5. Now we can change this as well. We can make this, how about 7.1? So now I expect this to say 9.1, and it does. So that shows that we can do some really simple math with Python. And we can also work with more than one variable. So let's set a variable b, and I'll set that to be 10. And now I can say a plus b, and maybe just to make things a little bit more interesting, I'll say a plus b star 2. The star here is for multiplication. So now I'll press Control-Enter and run this cell. And now we get 27.1. Let's make sure this makes sense. We have 7.1 plus 10, that would be 17.1. But then we're multiplying the 10 by 2, so that gives us 27.1. Okay, so that all makes sense. Now, if you are just getting started with Python, you have a tiny bit of code, it's fine to use variables that have a single letter like this. But once you start really programming in Python or any other language, you will find that using just one letter variables gets to be really confusing. It's really taxing for your memory because you have to remember what variable a means and what variable b corresponds to. So in practice, it's better to use more meaningful, longer variable names. So I'm going to set a variable name called Mike and set that equal to, how about 17? So let's see what happens if I say Mike times b plus 1. Okay, so that gives us 171. So 17 times 10 plus 1. Now I want to try this again. Mike, how about raised to the power of b? So to take powers in Python, you use 2 asterisks. So it looks like you're doing multiplication twice, but this is actually the special way to raise powers. So let's say Mike to the power of b. Now that's going to be some really astronomically large number. It's 17 to the power of 10. So that's this number, whatever that number is. But hey, what happened to this number? We lost that one. That doesn't show up anymore in the output here. So it turns out that Python only prints out the very last thing in a given cell. Now, if you want to print out multiple results within the same cell, you can use the print function. So we write print and then open parentheses and then close parentheses at the end of the line. So now we're going to get this answer from print, and then we get this output from the last line. Now you can see this doesn't say out, and this does say out. So in fact, I'm going to write print here again. And now we don't get any out messages. We just get these things printed out. Now I prefer this kind of visual formatting. I think this looks nicer than having something that looks like this, but that's just my preference. The important thing to know is that if you want to output multiple variables, if you want to inspect multiple things inside the same cell, you need to use the print function. And the way that works is you just type the word print, and then in between the parentheses is the thing that you want to print out. Now, let's say I want to go back and change some of these variables here. So I'm going to change b to be 0. And I want to change b to be 0 because that's, interestingly enough, that's going to give me 0 or 1 for both of these expressions. So now I change this to 0. You can see it's 0. And now I'm running this again. And I get exactly the same result here. So what is going on? Well, this is like what I said in the beginning of this video, that this is just some text on a screen. This is not anything that gets stored in Python until we actually run this code. So we have to press Control Enter again, run this code again, and now Python is going to overwrite the previous value of b with what's specified here. So then I can run this again, and now the numbers here change because I've changed b from running this code again. Okay, so now you can see we only have these two cells here, and I was pressing Control Enter. So I'm going to show you another keyboard shortcut here for creating a new cell. So we're in this cell. I'm going to press Shift Enter instead of Control Enter. That runs this line, this cell of code, and then it gives me a new empty cell, a blank cell underneath. Okay, what I want to show you now is that we can create variables that are strings as well. There's in fact many different types of variables in Python. So these are numeric variables because they're storing numbers. There's some more subtleties here as well. This is an integer and this is a floating point decimal. But for now, it's sufficient to know that these are numerical. So now I want to create some strings. So let's say I'm going to create a string called greeting, and it's going to say, hello, my name is, and then I run this, and of course nothing happens. We don't get any output. Now I could print this out. I could say print greeting, and it says, hello, my name is. Now, different people in different cultures have different customs, of course, but I believe this is a little bit rude. You know, you don't just walk up to someone and say, hello, my name is, and then walk away. Instead, you have to tell them your name. So let's say my name. My name is Mike. So how do I say, you know, I want to print out here, hello, my name is Mike, but these are two separate variables. So we maybe try doing something like this. Let's see if that works. Okay, so first of all, this illustrates one of the ways that you learn programming is you just take a guess and you try it and see what happens. Sometimes it works, very often it doesn't, but when it doesn't work, hopefully you learn something. So here we get our first error message in Python. This says invalid syntax, so clearly it doesn't like something here. It turns out that all we have to do here is add a plus sign. So we are not really adding greeting and name. That's what we were doing up here, but instead we are concatenating them. So this is a concept in computer programming called overloading. So we have exactly the same symbol, the same character, but it has different meaning depending on the context. So that's called overloading. Here, the plus sign means addition, like with math, and here it means string concatenation. So now we can run this again, and look at that beautiful result. Hello, my name is Mike. But you know, we need a punctuation mark here. So I want to add a punctuation mark. I'm going to say plus, and now we could create a variable that would be just a period, but instead I'm going to input it directly into this print function here. So plus, and then how about an exclamation point like this? So, hello, my name is Mike. This looks nice. All right, so we're making some pretty good progress here. There's one more thing that I want to introduce you to, and then I will give you the assignment for the end of this video. Yes, there's an assignment. There's an exercise at the end of this video. So let's say I also want to print in my name. So I'm going to say age equals, I'm too shy to tell you my actual age, so let's just say that I'm 10 years old. I know I have a very deep voice for a 10-year-old, but that's okay. So now I want to say, hello, my name is Mike. And then on this next line, I want to say, I am. And then it's going to be something, we know it's going to be age plus years old. By the way, notice that I'm putting spaces in here because otherwise we're not going to get any spaces in the text. So let's try this. And we get an error. The error message says, must be str, not int. So what do these mean? Well, sometimes the Python error messages are really easy to interpret, and sometimes they're a little bit less friendly or useful. So as you work with Python more, you'll start to be able to interpret these a little bit better. This says that what we're inputting here must be a string which means characters like this, letters inside quotes, and not an integer, which is what we actually have here. This is a number, this is an integer. So basically Python is saying, you know, I'm working with strings here. I don't know what to do with this number. So what we need to do is convert the number 10 into the string 10. And we can do that using a function called str. Notice also that you have these special functions and they turn green. The font turns green instead of black. So let's try this again. All right, so this is pretty cool. We can say, hello, my name is Mike, and I am 10 years old. Now, obviously, this is not like some amazing, super awesome, advanced programming, but this is a great way to get started. Okay, so now for your assignment. This is your homework problem. So in this assignment, I'm going to write out a message, and you are going to have to fill in the rest of the blanks, basically, to get this message to work. Okay, so here's some text. So what I want you to do after this video and before starting the next video is to basically copy all of this. So you want to write all this stuff down on your screen, and then you can try running this. You see, it's just not going to work for many reasons. So basically you have to just fiddle around with this code until it produces a message that looks nice and that you are happy with. And along the way, you can inspect some of the things that I've put in here that I haven't told you about. So you're going to have to play around a little bit and see if you can figure out what these various things mean based on what you see in the output. I'm going to start here by introducing you to a new variable type. This is called a list. I'm going to create a number list, and it's going to be just a list of numbers. How about something like that? So you can see it looks a little bit like the variables we created in the previous video, where we specify the variable name and then the assignment, the equals sign. But now we have multiple numbers. Now it's important that all of these numbers are separated by commas, and the whole thing is encased in square brackets, not parentheses and not curly brackets, but square brackets. So this gives us what's called a list. So we can see what it looks like here. So this is our list. And in this case, it's a list of numbers. Now, the list type, this variable type in Python, is pretty versatile. You can do a lot more things with lists than just storing individual numbers like this, but that's sufficient for now. Now, hold that in mind. What I want to do is show you that the basic Python version is really limited. There's a ton of stuff that we cannot do with basic Python, and that's why we need to import modules that are more specialized for different areas of processing. So for example, let's say we want to take the absolute value of -5. So we know that the absolute value of a negative number would, or the absolute value of a number in general, is its distance from 0. So the absolute value of -5 should be 5. Now there is a function called ABS for absolute value, and that does indeed return 5. So that's the correct answer. Let's say we wanted to do something else. What if we want to take the square root of 4? Now, I'm just guessing that the square root function might be sqrt. But you can already see it's probably not right because this turned green and here we have black text. So it turns out that Python actually doesn't have a square root function. How about let's try something else? What if we wanted to take the average of all of these 5 values? So, you know, the average, we sum them all up and then we divide by the number of numbers. So you could try something like average of num list, and that's not going to work. Oh, maybe it's called mean. No, but that also doesn't work. It turns out there is no function in Python to compute the average in the base environment of Python. Now, you're probably thinking that Python is totally worthless. You know, how can we use a program if we can't even compute the average of numbers? Well, it turns out that in Python, there are many what's called modules, or sometimes called toolboxes, that allow us to do a lot of other kinds of processing that is not with functions that are not in the base environment. So here's how we import a module. We type import and then the name of the module. And in this case, I'm going to be using something called numpy. And now I'm going to write as np. So there is an entire module. It's a set of functions. I don't know how many functions there are in NumPy. It's got to be hundreds. And we are now importing the NumPy module. So we're going to import all the functions inside NumPy into our current workspace of Python. And I'm going to call this NP. So let me show you what that does. So now mean still doesn't exist. It's not a thing. But mean is a function that's inside the NumPy module. So we have to type np dot. So this tells Python that we are going to look for this function not in the base environment of Python, but instead inside the NumPy module. And now we get an answer. So it turns out that the average of these 5 numbers is 2.8. And, just from looking at the numbers, that seems pretty plausible. And of course, NumPy also has a square root function. So we can take the square root of 4, and that gives us 2. As I mentioned, there are many, many functions inside the NumPy module. I'm going to introduce you to another one. That's called linspace. So the function linspace will create linearly spaced numbers between the first number, let's say it's 10, and the second number, sorry, I meant 1, and then the second number, which is 10. And then how many do you think we should do? Shout at your computer screen. Maybe I'll hear you in the past. How many numbers do we want between 1 and 10? How about 7? I think I heard someone say 7. Okay, so now I'm going to run this. And this gives us an output, which looks a little bit different from the kinds of outputs we've seen before. This is something called a NumPy array, but you can see it's really, really similar to a list. It's almost the same thing as a list. It's kind of a special case of a list. So we get 1, 2, 3, 4, 5, 6, 7 numbers, and the smallest one is 1, and the largest one is 10. Now, you might be wondering, how do I learn all of these functions that are available in all the modules in Python? Well, the answer is nobody knows all the functions that are available in Python. And the more common ones, the ones that are more relevant for what you're working on, those you will eventually commit to memory just by using them over and over again. And other ones, you just, you know what you want to do in Python, and then you look it up online and you find it really simply. Now I want to show you another way that you can get help on these functions. So if you know what the function is called, but you're not really sure what the inputs are or how the function works, you can click with the cursor inside the function, inside the parentheses, and then you press Shift Tab on your keyboard. And that opens up a little tiny window which you can expand with this plus sign. And this is called the help text or the doc string. And basically this tells you how to use this function. So the first input is the start. The second input is the stop. And then if you see inputs with an equal sign, that means that these are optional. So the default value for the number of steps between start and stop is 50. So if we don't put anything in here, then we're going to get 50 numbers between 1 and 10. Or we can add a third input. And, well, okay, this isn't very interesting because there's only 2 numbers that are linearly spaced between 1 and 10. But I think you get the idea. So maybe this is an important array. This is an important output that we need to use in the future. Now it's a little bit tedious to have to type this thing over and over and over again. So instead what we can do is create another variable and set that equal to the output of this function here. So let's create a variable. How about let's call it fun out. So fun because it's the output of a function, and also I'm having a lot of fun here. I hope you are too. So let's see, I'm actually just going to copy and paste this here. And then this is just another reminder that we have code that no longer gives any output here because there's other code after it within the same cell. Okay, so now we have this fun out variable, so we can look at it. We can say fun out, and not terribly interesting. It's the same thing as this. And we can also use this in mathematical expressions, just like we did in the previous video. So I could say fun out plus 2, and now we get numbers that go from 3 to 12 instead of from 1 to 10. All right, so that was like a mini crash course on importing NumPy and using NumPy. Now it's time for the assignment. It's time for your homework. So there's 4 parts to this assignment. So part 1 is going to be to create, let me just get this a little bit higher on the screen. So part 1 is to create a list of 15 numbers from 4 to 100. And then step 2 is going to be to round those numbers to the nearest integer and store in another variable. Now, I have not told you in this video or in the previous video how to round numbers to the nearest integer. So you have two options for figuring out this part of the assignment. Either you can just guess and start playing around with function names that you think might do what you want. And if that doesn't work, or if you have difficulties understanding it, then 2, go to the internet and just search for how to round numbers to the nearest integer in Python. You will be amazed at how quickly you get the answer. Or maybe you won't be. The answer to basically everything is out there somewhere on the internet. You just have to find it. Okay, then you want to print out number 2. Basically, you want to print out these numbers rounded to the nearest integer. And then the final step that you want to do here is to print out the square root of each number in the list. So each one of these from these. In this video, I'm going to introduce you to the matplotlib module. This is the main way of visualizing data in Python. So we're going to get started just by importing straight away. So I'm going to write import, and then the module is called matplotlib. Now we don't actually need the entire matplotlib module. We need only one section of it. It's like a sub-module. So that's called .pyplot. So we write import matplotlib.pyplot. Now, this is a lot to write. So, in the previous video, you learned about numpy. Now, numpy isn't so much to write, but imagine if you had to keep writing all this stuff over and over and over again. So instead, we write import as plt. It's a pretty standard shortcut or abbreviation for matplotlib.pyplot. And now I'm also going to import numpy as np. Now notice that I'm putting all of the import statements all the way up here in the first cell at the top of the code script. This is common procedure, and it's a really good idea because then, that kind of helps you organize your script. It helps you know right from the beginning of the script which modules are being used in here. Now I'm going to add something else. It's a little piece of code that's called a comment. So this comment is going to be import modules. Now notice that this comment is, so the font is a different color, and it's also in this italics format. So it looks different from the rest of the code. Now when you have a hashtag in front of a line of code, then Python just completely ignores that line. Python is not going to try to interpret this as code. So that's why this is called a comment. These are for, comments for you to remind you of what the code is, comments for other people to help them read your code. And of course, I've already shown you comments in previous videos, particularly with listing the assignments, but I didn't actually define what they were yet. Okay, so import these two modules. And now let's just do some basic plotting. So I'm going to write plt dot, because the function that I'm going to call here is not in the base environment in Python. So it's only in matplotlib.pyplot, which we're abbreviating as plt. So plt.plot. Now, the way this works, the way the plot function works, is you input the x coordinate and the y coordinate. Now I'm going to press Control Enter on the screen, and now we see a plot. So we see the axes here, and the axes, the coordinates look right. It's 1 and 3, but we don't actually see anything in the plot. So what's actually going on here is that Python drew a line, but because that line is just a single point, it's actually totally invisible. So, kind of technically it's there, but we can't see it. So I'm going to add an optional third input, and that's going to describe the characteristics, the visual properties of the line. So I'm going to make it a circle. So we write O for a circle. So there we get a dot. Now there's other options that you will become more familiar with as you continue using Python. There's circles and squares and triangles and stars and all sorts of things. I'm going to go back to making a circle, and I want to change the color. So I'm going to set this to be red. So R for red. Again, there's a lot of other options you will learn as you continue learning Python. For example, K is for black, but I'm going to stick with red for now. So now you can also see we get this output here. So I often write plt.show, and then we just get the plot. Now, depending on which version of Jupyter you're using and how exactly you're, which environment you're using for Python, you may or may not need this. So in the standard current modern Jupyter notebook, you don't technically need to use plt.show, but it's often nice for other reasons as well. Okay, now plotting in Python would be pretty depressing if all we could do was plot one dot at a time. So what I'm going to do now is plot multiple dots at the same time. So I'm going to introduce you to a new function in the numpy module. It's called arange. Now arange allows us to specify a range of numbers, and we're going to go from -9 to, now it looks like we're going to go to 10, but let's see what this actually does. So I'm going to print out x, and although, so we start from -9 and then we get all these numbers, but then it goes up to +9. So this is a little bit of a quirky way that Python works. Sometimes it takes a little bit of getting used to these idiosyncrasies, but when you use the numpy function arange, then the second input is actually one past the number that it goes up to. So if you actually wanted to go from -9 to 10, then you would need to write 11 in here, and then you get numbers up to 10. But I'm going to stick with going up to +9 here, because that's going to give me, I like this symmetry here. Okay, so now I'm going to define a mathematical function. I'm going to say y equals x squared. Now you might remember what this function looks like, x squared. It's going to look like a smiley face, basically. That's because these numbers are negative, so when we square them, they get positive, and when we get closer to 0, the function gets closer to 0. The numbers, the y values, get smaller. So let's plot this. I'm going to say plt.plot x comma y, and let's make this a red. Now I'm not specifying a red circle, just red. So this is actually going to give me a red line. So there you go. Here's a red line. And let's say we want to plot something else on top of this in the same plot. No problem. We can plot multiple things on the same plot. It's really easy. All we have to do is repeat this command. So I'm going to write plot.plt. And now I also want to show you that in this plot function, you can directly apply some arithmetic. So let's do y divided by 2. And I'll make this green squares. Okay, so then we see we get two things on this plot. So I don't know what you think this looks like. Maybe it's a big smile and these are teeth or something, a big cartoon teethy smile. Anyway, so what I'd like to do next is show you how to plot not a set of numbers here, but just a single line that goes from one point to another point. Well, the answer of how we get it is kind of already embedded in here. So x is a vector and y is a vector, and it's changing over space here. So what we want to do to plot a line is just specify the two x coordinates for the starting and ending points and the two y coordinates for the starting and ending points. So let's say I want to create a plot that goes from 0 to 3 on the x-axis, and then from -1 to +1 on the y-axis. So let's see what this looks like. So here we have, on the x-axis, we're going from 0 to 3, so that's these two numbers here. And then on the y-axis, we go from -1 up to +1, so that's these numbers here. So that's how you create a line in Python. You specify the start and the stop points for x, and then the start and the stop points for y. So now I'd like to add another line to this. So let's see, plt.plot, how about let's go like -2 to 0, and maybe -4 to 1. I'm just kind of making up these numbers. All right, so that looks pretty neat. We get two different lines here, but which line corresponds to which, or which of these lines corresponds to which line of code? Well, we could kind of look at the values and look back at here, but it's possible that you're going to send someone this graph. Maybe you export this as a file and you're going to email this to your grandmother. So you need a way to label these lines so your grandmother knows which line corresponds to which label. So to do that, we're going to add another optional input here. It's going to be label equals, and I'll call this, I don't know, first line. And then here I write label equals second line. All right, so let's run this code again. Ooh, and nothing happened. That was pretty disappointing. Well, so what we need to do is activate the legend. So we specify the legend labels here, but we need to tell Python to activate the legend. So we type plt.legend without any inputs. We don't need any inputs here because we've already described what each legend label is going to be. And now we get the legend. Okay, and now I just want to show you that the location of where you place this show line of code is important. So what I'm going to do is cut this and paste it here. So I'm just swapping the order here. And now we actually get a little warning message, and then we get two axes here, two plots. So what happened here is all the lines of code that we have before the plot.show, that all goes into one plot. And as soon as we call plot.show, then we're telling Python to create a separate plot. So everything that comes before this is one plot. Everything that comes after this and before the next plt.show or the end of the cell, that's going to go in a separate plot. So you can take a moment and, just play around with this. For example, you can stick it up here and you can see that creates the first line and that creates the second line. Okay, but obviously that's not really what we want. At the end of the day, we want a plot that looks something like this. Now I'd like to introduce you to how to visualize images using Python. So let's start with matrices, because matrices are actually represented as images in graphics. So let's see, we're going to start by creating a matrix. Now this is the first time I'm really mentioning this term matrix here in the course. I'll give you more of an introduction to matrices in a few videos. But a matrix is just like a spreadsheet of numbers. It's a table of numbers. So I'm going to use this function numpy.random.randint. So this is going to create random integers between 0 and 9. Remember, this is an exclusive upper limit, just like with numpy.arange that we saw earlier. And we're going to make the size of this matrix be 4 by 5. So let's see what this matrix M looks like. So here we get a numpy array, and you can see that it is 4 by 5. So there's 4 rows and 5 columns. Again, I'm going to talk about matrix and matrix sizes and things like that in a few videos from now. But you can see that this is just a bunch of integers, and it's a 4 by 5 matrix. So we can keep running this over and over again. The size of the matrix stays the same because these numbers are fixed here. But the numbers in the matrix, these values, are changing every time I run this code. And that's because we are generating random integers, randint, random integers. So it looks different every time. Okay, so we can visualize this matrix like this. Just look at the numbers. Now, for small matrices, that's fine. But once you get to larger matrices, it's not really feasible just to print out the, if you have like a 400 by 800 matrix, you can't just print it out and look at all the numbers. So instead, we are going to create an image. So it's a plt.imShow x. So this is for image show, and then plt.show. So now we have a matrix, which is an image. So each of these pixels, each one of these squares corresponds to one item in the matrix, and the color of each square corresponds to the value. So you can see at the bottom row, we have 2 zeros and then a 9 at the end. Then in here, we have 2 very dark blues and a bright yellow. So you can see that the color in each cell here in each little box maps onto the value of the element in the matrix. Okay, and so now we get to our assignment. So in this video, you learned about making lines, you learned about drawing lines on plots, and you learned about drawing images. So what you want to do now, at the end of this video, is make an X going through this matrix here. So you want to create a red X, like you're crossing out this matrix. So you need one line that's going to go from here to here, and then another line that's going to go from here to here. Now that you have a bit of a grasp on using Python, I'm going to start introducing you to some concepts in linear algebra. So let's start with vectors. A vector is an ordered list of numbers. So this is a vector. Now, these two vectors have the same number of numbers, and they have all the same numbers, but they're in a different order. So these are actually not the same two vectors. So the order is really important for a vector. So it's one vector, this is a completely distinct vector. However, they are both three-dimensional. We call the dimensionality of the vectors the number of numbers, or the number of elements. So 1, 2, 3 elements, so this is a three-dimensional vector. Here you see some more examples. This is a two-dimensional vector, and this is a 1, 2, 3, 4, 5-dimensional vector. Now, vectors can have different orientations. They can be standing upright like this, in which case they're called column vectors, or they can be lying flat on the ground like this, and then they're called row vectors. Now, these are still all vectors. They just have different orientations. So they're upright, and then they're column vectors, or they're laying flat, and then they're called row vectors. So I call this the algebraic interpretation of a vector because we're looking at numbers. There is also a geometric interpretation of vectors, and this is no different from the algebraic definition. It's just a different way of thinking about it. So if we take our vector, this is a two-dimensional row vector, and we can draw a line that goes from the origin of a two-dimensional space to the coordinate at 1, 2, which is the first element, and then the second element. So this is a line here, but it's representing a vector. So you can see that this geometric interpretation works for up to 3 dimensions. But in the previous slide I showed you a 5-dimensional vector. So how do we draw a 5-dimensional axis space? Well, we can't. So the geometric interpretation of vectors is useful when you're working in 2 or maybe in 3 dimensions, and after that we switch back to thinking about it algebraically. Now I want to introduce you to a mathematical operation on vectors, which is called vector scalar multiplication. So you now know what a vector is. It's an ordered list of numbers. And a scalar in linear algebra just means a single number. It's a bit of a fancy term just for a number, but you will see in the next slide why we call these things scalars. So a vector is a list of numbers. A scalar is just a single number not embedded in a list. So to multiply a scalar by a vector, it's really simple. You just, so here's an example. You just multiply the scalar by each individual element in the vector. So the scalar vector multiplication of 7 and this vector becomes minus 707. So we just multiply the scalar by each individual element. That's pretty straightforward. Okay, now I want to show you the geometric interpretation of vector scalar multiplication. So here I'm just defining some new vector to be the vector v multiplied by the scalar lambda. This is a Greek lowercase character lambda. So that looks something like this. So we would get, so this is our vector v here in blue, and then the vector w in this case is longer. It's this yellow line. Now if lambda is greater than 1, then you're going to stretch this vector. You're going to make it longer, but it points along the same line. And if lambda is between 0 and 1, so if it's greater than 0 but smaller than 1, then the resulting vector, so the result of scalar vector multiplication, is going to be smaller than the original vector. So that you see here. And the third possibility is that if the scalar is negative, if it's less than 0, then you're going to take this line and spin it around 180 degrees. Now it's interesting because you can see that the line, the resulting vector is still along the same line. If you think about a line going from, all the way down here to all the way up here, the scaled version of the vector is always on that same line. Sometimes it's longer, sometimes it's shorter, sometimes it's twisted 180 degrees, but it always stays on this line. Now, you might initially think about creating a vector as a list, which I've already introduced you to before. So let's say, 3, 4, 5, and how about go back down to 2? So this kind of looks like a vector. This looks really similar to the vectors that I showed you in the slides. And let's come up with a scalar, and let's just make that 2. So now let's say, I told you about vector scalar multiplication. So you might expect this result to be, 6, 8, 10, 4. However, when we run this, what we actually get, okay, well, here we see a little asterisk here. That means that Python is getting hung up on somewhere. It sometimes happens when you're using Python online. The server might be a bit busy or something. So if you see something like this, Python isn't producing a result, you can click on kernel and restart and clear output. That will just clean up everything and start again from scratch. Now that does mean that you will need to rerun all of the code that you've already run, including importing these modules. Okay, so now it turns out that what we get is not what we expected. Instead, we get a vector that seems much longer, or a list that is much longer. And in fact, when you see what's happened here, Python has repeated this vector twice. So we can test that idea by saying 3, and now we get this repetition 3 times. So 3, 4, 5, 2, 3, 4, 5, 2, 3, 4, 5, 2. So it turns out that although this list looks like a vector, Python does not treat this as a vector the way we want it to be like a vector. So instead, we're going to convert it into a numpy array. So we type np.array, and then in parentheses, and now this variable vec is no longer a list. Instead, it is a numpy array, and a numpy array is what we think of as a vector. So now we can run this, and now it works as expected. So 3 times 3 is 9, and then 12, 15, and 6. Next, I'd like to show you how to plot these vectors in Python. Now, you actually already know how to do this from the previous video, so I can go through this rather briskly because this isn't a whole lot of new information here. However, we're not going to be able to use this particular vector because this is a 4-dimensional vector. We would need a 4-dimensional axis to be able to plot this line, and Python is not quite capable of that, nor are we humans really capable of thinking about a 4-dimensional geometric space. Okay, so let's create a new vector. I'll call this vec2d, and this is going to be a numpy array, and let's just set this to be 1, 2. So you can already imagine what this vector should look like geometrically. It should start at the origin, and it's going to go 1 up or 1 over and 2 up. So it's going to be a line that looks something like this. Okay, now I want to come up with a couple of different scalars. This is basically to illustrate the concept that I showed in the slides a moment ago. Oops, S3 equals -1. Okay, and then we need to start drawing this. So I mentioned in the previous video that to draw a line, you need to draw the x coordinate and the y coordinate. So what are the 2 x coordinates and the 2 y coordinates? Well, this is only showing 1 x coordinate and 1 y coordinate. So how do we do this? How do we figure out this problem here? Well, you might have guessed that the solution is to appreciate that this line starts at the origin, and these numbers actually tell us the endpoint of the line. So we plot 0, vec 2d, and how do we actually access just the first element? I haven't taught you about that yet. So we don't want the entire vector, we just want the first element in this vector vec2d. So the way we do that is by something called indexing. So the way this works is you type the name of the variable, and then you use square brackets like this. It's important that these are square brackets. We're not using parentheses like this. We're not using curly brackets like this. This is just square brackets. And then we indicate the number that we want to access. So this is the first element. So let's try writing 1 and see what happens. And now we get a 2. So what is the deal here? Python doesn't know how to count? Well, so kind of. In fact, Python starts counting at 0. So this is the 0th element. We, in human language, would call this the first element, but Python calls this 0. And that means that this is the 1th, or the first element. So vec2d square brackets 0 gives us the first element. And then number 1, index number 1 is actually the second element, and index number 2 doesn't exist. So this only has 2 elements. So index number 2 is actually getting the element in the third position, and there is no element in the third position, so that's why we get an error here. It's a little weird. It takes a little while to get comfortable with this way of starting to count at 0, but that's how Python works. Okay, and that tells us our solution here. So we want to say vec2d 0, and this is the x-axis coordinate, and then we need the y-axis coordinate, and that also starts at 0. And then it goes to vec2d, it goes to the second element of vec2d, which is actually index number 1. Okay, and then I'm going to make this be a blue line with squares, and I'm also going to put a dash here. Now let me show you what that does. So here, if we didn't have a dash here, we would get 2 dots. This is the dot for the start of the line and the end of the line, but I want to have the squares here and a line between them. So I use B for blue, S for square, and the line for a dashed line. Okay, now I am actually going to copy and paste some code in here because there's a lot of code that isn't really any, so all this code is nothing you haven't already seen. And just it's just writing out. It looks like it's a lot of stuff, but this is the first line to create this blue line. And then we have S1 times. So now I'm just doing scalar vector multiplication the way that I showed in the slides. Now there's a couple of other things that I haven't introduced you yet here. So this line makes the axis be square. You can see it's a square instead of being a rectangle. If we comment this out, then we have a rectangle here. So here we get a square plot. This sets the x-axis limit and the y-axis limit, in both cases to go from -4 to +4, so -4 to +4 on both x and y. And this activates the grid, that's these gray lines here, and then legend you already know. Cool, so that's about drawing vectors and working with vectors. Now it's time for your homework. There's another assignment, always assignments at the end of these things. So your assignment is multifaceted. So what you want to do is create 2 vectors, and these should be 2-dimensional vectors because you want to draw them in a plot like this. So to create 2-dimensional vectors, now you can specify the numbers on your own, or you can create them as random integers. I've already shown you in a previous video how to create random integers. Okay, and then what you want to do is plot each vector, and then you want to plot vector v1 plus vector v2, and then you want to plot vector v1 minus vector v2, and then you want to plot vector v1 times 4 plus vector v2 divided by 2. So there's actually going to be quite a lot of lines in this graph that you're going to make here. Now this is interesting because I haven't actually told you yet how to add and subtract vectors, but it turns out that adding and subtracting vectors is really simple, and the way that you're thinking of it is probably the correct answer. So to add vectors means you just add each corresponding element of the 2 vectors. Same thing with subtraction. And then here, just to make sure this is clear, this is actually turns out to be 1 vector. What we're doing is combining 2 different vectors into 1 resulting vector. This is called a linear combination of vectors. It's very important in linear algebra. The dot product is one of the most important operations in all of linear algebra. It's super important, and you see it all over the place. And so in this video, I'm going to introduce you to the vector dot product. You can see there's several different notations that are commonly used in the literature that kind of highlights the importance and ubiquitousness of the vector dot product. The notation that you most often see is something that looks like this. So these are the 2 vectors, vector A and vector B, and there's a superscripted T that's in between them. This is called the transpose operator, and I'm going to tell you all about the transpose operation in a few videos from now. But for now, suffice it to say that the dot product is indicated by A transpose B, or A superscript B, where A and B are 2 vectors. So what is this mysterious dot product, and how do we compute it? Well, it turns out that the dot product is really simple to compute. All you do is take your two vectors. First of all, you make sure that they are the same dimensionality, so the same number of elements, and that's the case here. They both have 5 elements. And then what we do is multiply each corresponding element and then add up all of those individual multiplications. So the dot product between vector v and vector w is 1 times 2 plus 0 times 8 plus 2 times minus 6 plus 5 times 1 plus minus 2 times 0. And that gives us a total of minus 5. So notice that the dot product between two vectors is always going to be a single number, and that's because we do all these pairwise multiplications and then sum. So in the end, the dot product is always just one number. It's a scalar, regardless of how many elements are in the original vectors. And here you can see that the dot product is not defined for two vectors that have different dimensionalities. So, you can multiply these numbers here, but then you get here, there's no corresponding element in w, so the operation fails. Okay, so here we are, and actually we don't really need matplotlib in this particular video, but that's okay. We certainly do need numpy. So let's see, I'm going to create two vectors and then compute the dot product between them. So numpy.array, let's say, 4, 5, 6, 2. And let's create another vector, numpy.array, and let's make this one like minus 4, 3, and 0. Okay, and now to compute the dot product between them, now I explained it in the video, or in the slide, that you do all the element-wise multiplications and sum. But in NumPy, there is a function that does this for us. It's called numpy.dot. And all we do is input the two vectors here. Now, I can imagine you are screaming at your computer. You're throwing things at your computer screen because you know that this is not going to work. And this is not going to work because these two vectors don't have the same dimensionality. So let's see what happens when we try to run this code anyway. This is often a useful thing to do in programming, to run code that you know is going to give an error, or should give an error, and then you can see what is the error message going to be. So this tells us that the shapes or the dimensionalities are not aligned. Okay, so 4 does not equal 3, so we can either delete one number from here or add one number from here. Either way will work. I will add a 5, and now we get a dot product of 9 between these two. So now I'm actually going to get rid of one of these things. I think I'll get rid of this first minus 4, then they line up nicely like this. Okay, so now the dot product is actually a different number, of course, because the two vectors are different than how they were before. So let's create a new vector. Let's set this to b. I'll go back to minus 4. So minus 4, 3, 1, and now we can compute the dot product between vector 2 and vector 3, so that's no problem. Turns out to be negative. Dot products don't need to be positive numbers. They can be negative numbers. And now I want to show you multiplying a dot product with a different vector. So let's call this v4 numpy.array 0, 0, 0. Now this is a vector of all zeros, and you probably won't be surprised to learn that the term in linear algebra that we use for a vector of all zeros is the zeros vector. So what do you think is going to be the dot product between this vector v4 and this vector v3? Well, I'm sure you guessed it's going to be 0. No surprise there. We're just multiplying by zeros and then summing up all the zeros. So of course, whenever you multiply a vector by the zeros vector, you're going to get a dot product of exactly 0. There's just no other way around it. But it turns out that's not the only way to get a dot product equal to 0. So I'm going to create a new vector now. So let's call this v5 numpy array, and then we input. Let's make this 2, 3, minus 1. So now I'm going to compute the dot product between v3, which is this one, and v5, which is this one that I just created here. And let's see what this turns out. Oops, little typo there. It should be v5. Now this is pretty interesting because we saw that the dot product between these two vectors, so this vector and this vector, actually I'm going to just copy and paste this down here, just so it's easier to see these two numbers like this. So we see that the dot product between these two vectors is 0, which is initially a little surprising because none of these elements are actually 0. So we can do this math quickly in our heads just to confirm. So 2 times minus 4 is minus 8, and then 3 times 3 is 9, so minus 8 plus 9 is plus 1, and then minus 1 times 1 is minus 1, so then that gives us 0. So we can have a dot product between two vectors, neither of which is the zeros vector, and that dot product turns out to be 0. Now this is a really special thing. It's called orthogonal. So we say that vector, I'll write this whole thing out, vector v3 is orthogonal to vector v5. Orthogonality means that so this is the definition of orthogonality, that two vectors have a dot product of 0. And that leads us to the assignment for this video. So your homework assignment here is so let's see. So step 1 is going to be to come up with 3 vectors, and these should be 2-dimensional vectors because we're going to plot them. So you want 3 distinct vectors that are in a 2-dimensional space, so they have 2 elements, and you want to create the vectors such that 2 of them are orthogonal, but not orthogonal to the third. I should say neither is orthogonal to the third. So 3 vectors. You can call them v1, v2, and v3, or you can call them anything you like. You can call them Mike, Bob, and Sally. So create 3 2-dimensional vectors and make sure that 2 of them are orthogonal, but that each of these 2 is not orthogonal to the third. And again, not orthogonal to another vector just means that the dot product is not 0. It can be any other number as long as it's not 0. And then what you want to do is plot all 3 vectors on a 2-dimensional plane. And this is important. Make sure the axes are square and equal. So this is like what I showed in the previous video, where I showed you how to create an axis that had the same x-axis limits as the y-axis limits, and the x-axis and y-axis limits go from the same positive to negative number. So it could be minus 4 to plus 4, or you might need to use different numbers depending on which vectors you come up with. But it should be the same number, negative and positive, and that the axis is square. So that's important because what you want to do with this exercise is make some discoveries about what orthogonal vectors mean geometrically. So you're going to discover something interesting about 2 orthogonal vectors versus the vectors not being orthogonal to the third. A matrix is a 2-dimensional collection of numbers. It's like a spreadsheet. When talking about the size of the matrix, we refer first to the number of rows and then to the number of columns. So this would be a 4 by 3 matrix. This would be a 3 by 7 matrix because there's 3 rows and 7 columns. So it's always in this order. You wouldn't call this a 7 by 3 matrix. It is a 3 by 7 matrix. The diagonal of a matrix refers to all the numbers that start from the top left entry and go 1 down and 1 to the right. So 1 down and 1 to the right, and this gives us the diagonal of the matrix. All the other numbers, these are called the off-diagonal elements. Now this particular matrix has 4 rows and 4 columns, so it works out that the diagonal goes from the top left to the bottom right. That's a special size of a matrix. That's called a square matrix when it has the same number of rows and columns, so a square matrix. But non-square matrices, sometimes called rectangular matrices, also have a diagonal to them. It's just that the diagonal doesn't go all the way to the bottom right corner, but it's still the same operation. We start at the top left and we go 1 down and 1 to the right. That's the next diagonal, and then that's the next diagonal. There are many special kinds of matrices in linear algebra, and now I'm going to introduce you to just a small number just to give you a little bit of a taste of these special matrices. This one in particular is called a symmetric matrix, and a symmetric matrix is a square matrix, so the same number of rows and columns, where all of the elements above the diagonal are mirrored with all of the elements below the diagonal. So you can see -1, -1, 0, 0, -4, -4. It's like, if you would print out this matrix on a piece of paper, you could fold that piece of paper along the diagonal, and then you fold this top part of this top corner over down to this lower corner, and you would see that these are all mirrored. So that's a symmetric matrix. Here we have a special kind of matrix called the identity matrix. The identity matrix has all zeros on the off-diagonal terms and all ones on the diagonal terms. So zeros everywhere except for the diagonals, where every diagonal element is 1. Now sometimes you see matrices with these dots in them like this. These are like continuation signs. It means that it doesn't really matter how many rows there are. There could be another 2 rows or 100 rows. There could be 5 more columns or 1,000,000 more columns. So this is showing the general form. So zeros on the off diagonals and ones on the diagonals. The identity matrix is so important in linear algebra that it gets its own special letter, which is the letter I. So anytime you see a capital boldface I in linear algebra, you know that that's referring to the identity matrix. Sometimes there's a little number down here, and that would indicate that this is referring to a 2 by 2 identity matrix. This is a 5 by 5 identity matrix. So it's the identity matrix with 5 rows and 5 columns, but more often than not, you just see with a capital I like this. The last special matrix that I want to introduce you to here is called the diagonal matrix. Now it's a little bit confusing because I already told you about the diagonal of the matrix, but that's this 1 minus 2, 5. That's the diagonal of the matrix, but this whole thing is called a diagonal matrix. And what makes this a diagonal matrix is that all of the off-diagonal elements are exactly equal to 0, every single one of them, and the diagonal elements are non-zeros. They can also be zeros, but only the diagonal elements are allowed to be non-zero. So here's an example of a square diagonal matrix. Here's an example of a non-square or rectangular matrix, which is also a diagonal matrix because all the off-diagonal elements are zeros, and the only non-zero elements are in the diagonal of the matrix. Now, of course, in the previous slide, I showed the identity matrix, which is a form of a diagonal matrix. So the identity matrix is a special case of the diagonal matrix. I'm going to show you how to create some of these special matrices that I've already introduced you to. So let's start with a identity matrix. So there's a really neat formula here called I. It's spelled I, like the eye in your face, but it actually produces the identity matrix. So we can write, for example, 3, and then we see the 3 by 3 identity matrix. Now, because all identity matrices are square, all identity matrices have the same number of rows and columns, so we don't actually need to specify separately the number of rows and the number of columns. And you can see this is the identity matrix. It has 1s on the diagonal and 0s on the off diagonal. So that's for the identity matrix. We can also create a matrix of all zeros. Now, the thing is that a zeros matrix does not necessarily need to be square. So we need to specify here that how many rows we want and how many columns we want. So I'm going to create a 3 by 4 matrix here, and you can see it's a matrix of all zeros, and there's 3 rows and 4 columns. Okay, and then there's one more function I'm going to introduce you to here, and that's called full. So what the full function allows us to do is create a matrix where we get to specify the size, let's say 5 by 2, and then we can specify a number to fill in the matrix. So this is going to be a matrix that's 5 by 2, so 5 rows and 2 columns, and Python is going to set every element to be 7, and that's because I pressed 7 here. So I could have said 17, so now we get a matrix of all 17s. So these are a couple of functions to create vectors. You can also create your own vectors, and I'm going to show you that now. So let's call this matrix M. It's a good letter for a matrix. numpy.array. So you can see we are starting here in a similar way to how we created vectors with numpy. And now the way this works for creating matrices is you have to use one set of square brackets like this to indicate the entire matrix, and then you need another set of square brackets for each individual row. So let's say 1, 2, 3. So this is going to be the first row, and then a comma, and then the second row. Let's make that 4, 5, 6. And then let's make a 3 by 3 matrix. So let's do 7, 8, 9. Okay, and then we can print out M and see what this looks like. Now, this is a little bit confusing. There's a lot of square brackets, and we have all 3 rows on the same line. Now, Python doesn't care. This looks fine to Python, but it's a little bit harder for human beings to read. So what I'm going to do is just press Enter here and just space this out a little bit. And then run this again just to show you that to Python, this is the same as how I had it before. But of course, to humans, this is more readable. So now we see the first row, the second row, and the third row. And then we see the outermost brackets for indicating that all 3 of these rows goes into one numpy array, one object. Okay, so that's a pretty quick introduction to matrices. Now we get to the assignment, the most fun part of these videos, I'm sure. So let's see, what you want to do here is create 3 matrices, and you need to specify their sizes. So one matrix is going to be 2 by 2. Another matrix is going to be also 2 by 2, but different numbers from this first matrix. And then you want another matrix of 3 by 2. So 3 matrices that have 2 different sizes. Now you can create these matrices to be numbers that you specify like this. You can create these matrices to be random integers like what I showed in a previous video. That's all fine. And then what you want to do is compute scalar matrix multiplications. Actually, there's 3 parts to this assignment. So this is step 1 is to create these matrices. Step 2 is to compute scalar matrix multiplication. Now, I have not told you in the slides how to implement scalar matrix multiplication, but I did tell you about scalar vector multiplication. So what you are going to do is discover whether scalar matrix multiplication is the same as scalar vector multiplication. Okay, and then step 3 is to add all pairs of matrices. So, if you call this M1, M2, and M3, then you're going to add M1 plus M2, M1 plus M3, and M2 plus M3. And again, I haven't yet told you how matrix addition works, how it works with adding 2 matrices, but you are going to be using Python as a tool to help you understand these concepts in mathematics and linear algebra. And you will discover in the process of step 3, you will discover an important rule about matrix addition. I've already mentioned to you this concept of transposing a vector or a matrix. So let's see what this operation actually means. So here we have a vector. This is a column vector. In particular, it is a 5-dimensional column vector. And we can transpose this column vector, and that converts this column vector into a row vector. Now, the important thing to know about transposing is that it doesn't change the elements themselves, and it doesn't change the ordering of the elements. So we have exactly the same numbers in exactly the same order. All we've done is change the orientation of this vector from a column vector into a row vector, and that's what the transpose operation does. Now, the transpose operation in general flips rows into columns and columns into rows. So transposing a row vector would get you into a column vector. This isn't necessarily only about going into a row vector. It's just about swapping whatever is the already existing orientation. So this is for transposing a vector. Transposing a matrix is essentially the same thing. So here we have a 5 by 2 matrix, so 2 columns, and we can transpose this, and that gives us another matrix where the first column corresponds to the first row, and the second column corresponds to the second row. Now, the only thing you have to keep in mind about transposing is you might be tempted to think about the transpose operation visually such that you are just like rotating this matrix 90 degrees like this. So imagine you put a pin in the 5 and you're just swinging this matrix up. That seems like a nice visualization, but it doesn't work, unfortunately, because that visualization would give you this column, this green column on the top row, which is not the case. So it's always the first column turns into the first row. And now you can also picture this the other way. So you can think about this as being the first row turning into the first column, and the second row turning into the second column, and so on. So now that you know about the transpose operation, we can actually come back and revisit this special type of matrix called a symmetric matrix. Now remember, I said that a symmetric matrix is mirrored across the diagonal. Now it turns out that what is special about a symmetric matrix is that the matrix equals its transpose. This is a really unique property. Most matrices are not like this, so only special symmetric matrices follow this pattern, have this definition. So we see that the first row is the same thing as the first column, and the second row is the same thing as the second column, and so on. You can do this all ways you want. So here's the third column, that's the same thing as the third row. So the definition of a symmetric matrix is a matrix equaling its transpose. So let's begin exploring the transpose operation with a vector. So I'm just going to define a vector exactly how we've been defining it so far. Let's say, I don't know, 2, 3, and how about -1? So I'm going to print out this vector, and then I want to print out the transpose. So to get the transpose, we can actually put a dot t at the end of the vector like this. So this is called a method on this object, but you don't have to worry about the fancy coding terminology. So we just print the name of the vector or matrix, and then a dot, and then a t for transpose. So let's see what this looks like. Well, this might not look like what you would have expected it to look like. So it started off as a row vector, so you might have expected this to turn into a column vector. Now the issue here is, although we are looking at this thing and interpreting it to be a row vector, internally Python, the numpy array of Python, doesn't actually encode the orientation. So Python doesn't see that this is a row vector or a column vector. It just sees it as a vector without any particular orientation. So therefore the transpose actually does nothing. So what we need to do in this case is add an optional second input where we specify that the number of dimensions in this vector is 2. And now, oops, sorry, it's not ndim, it's ndmin. I have to get the spelling right on these things. So now, and actually I'm going to put in an empty space here just to give us a little more room. So now we see that Python is representing this as a row vector and this, the transpose, as a column vector. And you can also see now that there are double square brackets. And this is similar to the matrix formatting that I introduced you to previously. So we have one outer set of square brackets for the entire matrix, and then we have one, like you call these inner square brackets for each individual row. So this vector here is a row vector, so it only has one set of square brackets here to indicate a row vector. And here we have a column vector, which actually means that there are 3 rows. So that's why there's this proliferation of square brackets here. Again, this stuff is a little bit confusing when you're first getting used to it, but when you work with Python more and more, then these kinds of, little weird idiosyncratic things will start making more and more sense. Okay, so that was for a vector. Now I want to show you the transpose of a matrix. So let's define a matrix. I'll set this to be random numbers. So numpy.random.rand n, and let's make a 3 by 3 matrix. So let's see what this thing looks like. So we have a 3 by 3 matrix of all random numbers. So this is a function rand n, and the n here means to create normally distributed numbers. So these are numbers that have an average value, an expected average value of 0, and a standard deviation of 1. And basically that just means that you are highly likely to get random numbers that are close to 0, and the further away from 0 you get, like these numbers, the less likely they are to be observed. So we can see here is, let's see, here we don't even get a single number larger than 1. So we run it again, here we get 2.8. So you can get these larger numbers relatively further away from 0, but they're just less likely to occur. Okay, so that's a 3 by 3 random matrix, but for doing these operations, we want to be able to look at the numbers pretty easily and see whether the transpose really did what we expected it to do. So I'm going to use a function called round, which I believe you might have already discovered earlier in the course when you had to have this assignment of rounding numbers to the closest integer. So now the issue is that these numbers are all so close to 0 that when we round them, we get basically just zeros and ones and minus ones. We might get it to possibly even a 3. That could happen, although it's not super likely. So I'm going to do basically just a little trick. I'm going to say 10 times these random numbers and then round them. And all that's doing is just giving us a broader range. It just spreads out the numbers a little bit more. Okay, so that's our matrix of random integers. And then here we get the matrix transpose. And then again, the main point is just to confirm that in the original matrix, the first row corresponds to the first column of the transpose matrix, and so on. You could look at this many different ways. So the first column of this matrix turns out to be the first row of this matrix. All right, so that is about the transpose operation. Now it's time for the assignment. I'm sure you've been looking forward to this all video. Now the principle here is the same as with the assignment in the previous video. So we are going to be, you are going to be using Python as a tool to help you understand concepts in mathematics. In particular, you are going to use Python to discover a question that is about the transpose. So we want to know, does the question is, what happens when we transpose twice? So we want to take a matrix. It can be one of these matrices or a vector, any vector or matrix. You can create a new one, transpose it, and then transpose it again. And what you should do is create 2 variables. So you're going to need, let's see, m is going to be the matrix, and then maybe you have another variable called mt, which will be the transpose, and then you want to transpose this matrix. So maybe you want to call that matrix mtt for matrix transpose transpose. And the question is, how does the transpose here, the double transpose, relate to this matrix and to this matrix? So that's what you want to discover. Basically, what happens when you transpose a matrix twice, or a vector, same thing. Okay, and then the second thing you want to do here is confirm that the transpose operation works on non-square, sometimes also called rectangular matrices. Now I already showed you an example of this in the slides, but it's nice to see it in practice in code. So basically apply the transpose operation, but instead of using a square matrix, apply this on a non-square matrix. At this point in the course, you have learned that vector and matrix addition and subtraction is pretty straightforward. It works the way you would expect it to. And multiplication by a scalar, so scalar vector multiplication and scalar matrix multiplication, is also pretty straightforward. Now we get to matrix multiplication. So that's multiplying 2 matrices by each other. Now this turns out to be quite a bit more complicated, and in fact it's beyond the scope of this short course to explain the mechanics of matrix multiplication. So instead, what I'm going to do in this video is teach you the rule for knowing when 2 matrices actually can be multiplied, because it turns out that not all matrices can multiply each other. So that's also unlike with normal numbers. Okay, so before we even get to that rule, we need to learn about a little bit of terminology, and that's not really how this shows how special matrix multiplication really is. So if A and B are 2 matrices and we try to multiply them like this, then we describe this as saying matrix A left multiplies matrix B, or you can say matrix A pre-multiplies matrix B. Conversely, you can flip it around and say B right multiplies matrix A or B post multiplies matrix A. Now the reason why we need to make this distinction here with the terminology is because matrix A times B is not the same as matrix B times matrix A. So if we would put B on the left, we are likely to get a different result. So that's also seems really weird coming from normal arithmetic because, 2 times 4 is the same thing as 4 times 2. But with matrices, it doesn't quite work like that. Okay, so this is about the terminology. And now let's get to the rule. The rule of when matrix multiplication is even valid. To determine whether two matrices even can be multiplied, what you have to do is line them up like this. So this is a visual representation, an abstracted representation of a matrix. This is a different matrix. And then we write down their sizes. So this would be an m by n matrix, so m rows and n columns. And this is an n by k matrix. So now there's n rows and k columns. Now, you look at these two, I call these the inner dimensions. They're the inner dimensions, just the way that they're laid out here when you line up these 4 numbers here. So rows, columns, rows, columns. Now, if these two inner dimensions match, that means if the number of columns in the first matrix is the same as the number of rows in the second matrix, then these two matrices can be multiplied. If these were not the same number, let's say this was, well, I'll show you examples on the next slide. But if these two sizes are not the same number, then these two matrices cannot be multiplied. Okay, so this tells you if the multiplication is valid. And then the size of the product matrix, which you already see here, corresponds to the outer dimension. So an m by k, this is going to be an m by k matrix. Again, two matrices can multiply each other only if their inner dimensions match. When you line them up, when you line up all the sizes, the 4 numbers of the sizes here. So rows, columns, rows, columns. So these two numbers have to match. And then if they match, the product, the size of the product matrix is given by the outer dimensions here. Okay, let's see a few examples. So here's a matrix A. It is 5 by 2, so 5 rows and 2 columns. And here's our matrix B. So the question is, can we multiply these two matrices? Is that a valid operation? And the answer is yes, because the inner sizes match. And so the resulting product matrix is going to be 5 by 7. Here's another example. Are these two, so now imagine these are like the same matrices. I just swapped the order. And now all of a sudden, these matrices can no longer be multiplied because the inner dimensions do not match. Again, that's kind of a weird thing to think about, that matrix A times matrix B is valid, but the exact same matrices, just swapping their order, is no longer a valid multiplication. Here's another example. So here the matrix product is not defined. This is not a valid operation. However, one thing we could do here is actually transpose this first matrix. Now remember, when we transpose a matrix, the rows turn into columns and the columns turn into rows. So that means that, matrix C is 5 by 7, but matrix C transpose actually becomes a 7 by 5 matrix because we've swapped the rows and the columns. So now this actually becomes a valid matrix multiplication. So with this in mind, I want to get back very quickly to the notation of the dot product. So you remember that I introduced the vector dot product as having this notation. And now we can briefly understand why that is the case. So we imagine that we start off with 2 column vectors and we transpose the first column vector, and that gives us a row vector over here and a column vector over here. So now the inner dimensions match, and the outer dimensions gives us the size of the resulting product, which is just going to be, well, 1 by 1, but it ends up just being a single number here. By the way, you can see that in the beginning of the video, I'm restarting Python here online. And that's because, as I mentioned in the beginning of this course, if you're using jupyter.org/try, this server will basically kick you off after, I think it's 15 minutes. So, I'd wait a few minutes between recording videos and then I'd do the slides. So it ends up that I have to reboot the Jupyter kernel here. So that's why I'm always starting from scratch. Okay, anyway, so what I want to do now is just create a few matrices and illustrate one of the concepts I showed just a moment ago in the slides. So I'm going to create a random matrix. So rand, and let's make this 4 by 5. And now I'm actually just going to copy and paste here, change that to 2, and yeah, so these are going to be 2 4 by 5 matrices. So now my question for you is, can I multiply matrix 1 by matrix 2? The answer is no, not directly, because when we line up their sizes end up being 4 by 5, and the second one is also 4 by 5. So the inner dimensions do not match. However, we could actually transpose one of these matrices, and that would allow us to multiply them. So that's what I want to do here. Now, how do we actually multiply two matrices? There's two ways we can do this. There's a numpy function for it. So it's numpy dot matmul, sort of matrix multiplication. And then we input the first matrix that we want to multiply, and then the second. And now we can confirm that this actually doesn't work. We're getting an error here. And we can see that Python is giving us an error. Here are the sizes. And the sizes of the two matrices, you see k and k have to match. And the resulting product size. So this says size 4 is different from 5. So we already know how to transpose a matrix here. So we do .t, and whatever these numbers mean, they're all random numbers, so we can't exactly interpret it. But we do see that we transpose the second matrix. So this was 4 by 5, and then this matrix becomes 5 by 4. So now the resulting product matrix is going to be 4 by 4, and we can confirm that here. Okay, and then I'm going to put in a space in here, and then I just want to show you the other way of multiplying matrices. Now it turns out that with an asterisk, that is multiplication for regular numbers, but not for matrices. So you can use either the function numpy.matmul, or you can use the @ symbol here. So then we use the @ symbol. I have to transpose this. And from quick visual inspection, it certainly seems that these two matrices are the same. And what I want to do now is just show you one of several ways to illustrate that two expressions are the same in Python. So I want to show that this produces the same output as this. And so one way we can do that is by subtracting them. And what would you expect the difference between these two matrices to be if they are the same? You guessed it, we expect the difference to be 0. In particular, we expect a matrix of all zeros, which is what we get. So we subtract this matrix from this matrix, or actually we're subtracting, this matrix from this matrix, and the result is all zeros, and that tells us that both of these methods are the same. They produce the same results. All right, so that is about matrix multiplication. So now I want to give you your homework problem. So the assignment, this one's going to be fun. I mean, they're all fun, but this one is also fun. So your assignment is to create a 3 by 3 matrix of integers. And again, it's convenient to make these matrices be integers just because they're a little bit easier to look at and quickly interpret, as opposed to these where you really have to it takes a little bit more effort to go back and forth and compare these two matrices. So you want to create a 3 by 3 matrix of integers, and then you want to multiply that matrix by first the identity matrix, and of course that has to be the 3 by 3 identity matrix, and then the zeros matrix, and then you want to multiply by that matrix's transpose. So this is going to be pretty interesting. Here you will discover an interesting feature of the identity matrix and what it means to multiply a matrix by the identity matrix. You can probably guess what's going to happen when you multiply this matrix by the zeros matrix, but it's good to confirm. And this will be interesting. You are going to discover an interesting property. And what I would like you to notice here is that the matrix product is going to be symmetric. So keep your eyes out for symmetry even when this matrix is not symmetric. Here's a pretty simple equation. How would you solve for x here? Well, of course, what you would do is divide both sides of the equation by 3, and that gets rid of the 3 over here, because 3 divided by 3 equals 1, and 1 is the multiplicative identity, because any number times 1 equals 1. So then we get x equals 1/3. We can also write that down this way. Instead of dividing by 3, we are multiplying by 3 to the power of minus 1. And when you have a number that's taken to a negative power, that just means you take the reciprocal. So 3 to the power of minus 1 is the same thing as 1 divided by 3, or 1/3. Okay, so that gives you this, and then we see that x equals 1/3, or x equals 3 to the power of minus 1. Now, you want to be able to do something like this in linear algebra. You want to be able to divide a matrix by another matrix, but it turns out that this doesn't work. There is no such thing as matrix division. That operation does not exist in linear algebra. So we basically leverage this that I mentioned in the previous slide. So some divided by 3 is the same thing as multiplying by 3 to the power of minus 1. So conceptually, what you want to do with matrix division is actually implemented by something called the matrix inverse. So this would be at matrix S times the inverse of matrix R. That's what this is called, the matrix inverse of R, and we put a minus 1 in the numerator, and then it's sort of the equivalent of this. Now, why do we need something like a matrix inverse? Well, let's imagine we have an equation like this, where this is a matrix, A is a matrix, X is a vector of unknowns, that's what we want to solve for, and B is another vector of numbers that we already know. So what we need to do to solve for X is isolate X on the left-hand side of the equation. Now we cannot divide both sides of the equation by A, because matrix division is not a real operation. It doesn't actually exist. But what we can do is left multiply or pre-multiply both sides of this equation by the inverse of A. So then we get something like this. So now here we have A inverse times A. And now it turns out that what is special about A inverse is that it's a matrix that multiplies the original matrix A to produce the identity matrix. And you discovered in the previous video, in the exercise, that when you multiply any other matrix or any vector by the identity matrix, you get exactly that same matrix or vector, just like the number 1. It's very similar to the number 1. So we can actually just get rid of this identity matrix over here. So A inverse times A equals the identity matrix, and that allows us to solve for X. Now this equation right here is the basis of a lot of things in statistics, like linear least squares, general linear modeling, regression analyses. So this equation is really important in statistics and in machine learning and deep learning and artificial intelligence. Now, the way to compute A inverse is actually a little bit complicated. There's a few different algorithms for computing it, and explaining those algorithms is beyond the scope of this short course. However, of course, in practice, we do it using a Python function. So let's have a look at that. So I'm going to start by creating a random numbers matrix. I happen to like random numbers matrices. I use them all the time. So let's make this 4x4 random matrix and call it M. Maybe I'll call it A just for a little bit of variety. So now I'm going to create A inv. That's going to be the inverse of A. And that will be numpy.linalg. So this is a different submodule inside the numpy library. So numpy.linalg.inv of A. So now we have these two matrices. I'm going to print them out. So print A, and then I'll print a space just for visibility, and then print A inv. Now the thing is, it's really hard to look at an inverse, particularly for a matrix like this, and see how the inverse relates to the original matrix. It's not clearly any relationship. In fact, the relationship is embedded across all the rows and all the columns. So instead, what I'm going to do to illustrate to you that A inverse really is the inverse of matrix A is multiply them. So I'm going to say, let's call this A inv A. And that is going to be equal to matrix A times matrix multiplication times A inverse. And then I'm going to print out, so let's see, print another little space here, and then print A inv A. And now we see that this doesn't immediately look like the identity matrix, but it actually is. So you see the diagonal elements contain ones, and all the off-diagonal elements contain, this looks like it says -2, but actually it's -2, and then there's this e minus 17. This is the computer way of expressing 10 to the minus 17. So in fact, this number is 0.0000000000000002. So this is basically 0 at the computer precision. This is computer rounding error here. So to get a better sense of this, what I'm going to do is visualize these three matrices using the IMShow function that I introduced you to in matplotlib towards the beginning of the course. So I'm going to do this a slightly different way. I want to create three matrices, and I want the three images to be all next to each other in a row. So I'm going to show you a slightly more advanced way of setting up multiple plots in matplotlib, which I haven't yet introduced you to. So I'm going to write fig comma ax equals plt.subplots. That's what it's called when we have multiple plots in the same layout. And I'm going to make this a 1x3 geometry. And then it's often useful to specify the figure size. So let's see. So we write x 0. So this is going to be what we're plotting in the first axis. IMShow m. And then x1 is going to be IMShow, oops, not m. A, I meant to say. A, and then here is going to be A inv. And then x2 is going to be IMShow A inverse times A. And then we can make a plot of this. Oops, plot not defined. Oops, right. I didn't import the matplotlib. Import matplotlib.pyplot as plt. And computers are sticklers for spelling, so you have to make sure you're spelling everything correctly here. All right, let's try this again. Brilliant. Here we see our matrix A. Here is A inverse, and here is A inverse times A. And you can see this looks like the identity matrix. It's all ones on the diagonal and zeros on the off diagonal. Okay, now I'm just going to put in some titles here to make this a little bit cleaner. So x0.set title. So this is matrix A. And then we have this set.title. This is matrix A. And I'm going to do something interesting here. This is a little bit of LaTeX coding. So let me just start it like this. So you see, this is not anything particularly special. It doesn't even look very nice. But watch what happens when I put a $sign surrounding this special code. So this caret symbol, and then in curly brackets, the -1. All of a sudden, it looks quite different, and the caret symbol indicates superscripting, and everything that's inside this curly brackets goes into the superscript above A. This is called LaTeX coding. I can write this out for you. LaTeX, it looks like this. LaTeX coding, and it's just a special way of getting Python to interpret non-standard letters. All right, so, and then the last one is going to be A inverse times A. So, oops, there's a typo here. I specified this to be 1, so it actually updated this title here. That should be 2. Now we get the third subplot, which is index value 2. So what comes next? Of course, it's the exercise for this video. It's the assignment. Here is your assignment. Now, up here, I said it's really difficult to see the relationship between the matrix and its inverse. You know, when you just look at the elements, it's hard to see how they match, and they don't really match element by element. And you also see that in these images here. So it's not obvious that this matrix is the inverse of this one. You really have to see them multiplied. But there is actually an exception, and that is for a diagonal matrix. So there's an interesting property of a diagonal matrix and the inverse of a diagonal matrix. And that is what you are going to discover in this assignment. So what you want to do is, let's see, you start by creating a vector. Create a vector, let's make it 3 by 3. How about that? 3 by 3 vector. And then you want to create a diagonal matrix from that vector. So you are just going to specify a vector. Oops, this was I meant to say 3-dimensional vector. So you're going to create a 3-dimensional vector, and a really simple example is just 1, 2, 3, something like that. And then you want to create a diagonal matrix where the diagonal elements of this matrix come from the vector that you specify. Now there's a function in Python, in NumPy, that will create a diagonal matrix when you input a vector. I'm not going to tell you what that function is because I want you to figure it out on your own. You have 2 ways to figure out what that function is. One is you can try playing around with different terms until you think you find something that works. Or 2, you just look around on the internet. I think it will take you no more than 30 seconds to figure out what the function is from the internet. Okay, once you've created that diagonal matrix, then you compute its inverse, and then you want to print out both of those matrices like this. And you will discover the interesting property of the inverse of a diagonal matrix. So you can pay attention to the elements of the diagonal of the inverse and the elements of the diagonal from the original diagonal matrix. Okay, that's one thing. And now there's a second part of this assignment, which is that it turns out that the matrix inverse is defined only for square matrices, so only for matrices that have the same number of rows as columns. And so to illustrate this to yourself, what you want to do is create basically any non-square matrix. You can make it 2 by 3. Create a 2 by 3 matrix, or whatever size you want, and try to compute its inverse. And you will get an error message, and you can see what that error message tells you.